All right, so to this issue of kind of heightening the conversation about resources to detail their specific social and political issues, then the issue becomes about sustainability. And the issue becomes about, what are we using these resources for? How important are these uses of these resources to our political and social structures? And where it is extremely important, we need to put additional effort in making sure that we're, maintaining that resource and extracting that resource in a way that is both economically feasible as well as sustainable. One of the most important ideas is this idea called intertemporal allocation, which is basically how do we think about resources over time? So oftentimes we may think about resources in sort of the current time period, and that's of course what's driving a lot of the private decision making is the current time period demand and supply for the particular resource. But because resources have these unique time components, we can't exhaust them over time. And with depletable resources, they're finite. They will be exhausted over time. I mean, oil, natural gas, metals, I mean, it may take a long time for us to exhaust them, but they will become exhausted. And then, of course, with your renewable resources, we want to make sure that our demand and supply is cognizant of those natural replenishment rates. So there's the dynamic efficiency criterion, which says that what we want to do is we want to maximize the present value of future net benefits coming from the resource. If we do that, then we're not just considering the current time period, we're also considering future time periods. So in other words, instead of thinking about the resource just in terms of maximizing the current period benefits, we want to think about extracting the resource, using the resource in a way that maximizes the present value of all future benefits as well, right? Not just now and not just while we're alive, but of course, while, when our progeny is alive and takes over for us. And the dynamic efficiency criterion says is that if you do this, if you actually maximize the present value of the future net benefits coming from the resource, then you will naturally treat that resource in a sustainable fashion. In addition to that, with respect to depletable resources, the dynamic efficiency criterion also offers what we would call a transition path to a substitutable resource. And we're going to talk more about that here in just a few moments. Heartwood Rule is sort of a particular guiding principle as it pertains to natural resources. This requires that a nation invest all of its earned exhaustible resources currently extracted, the rents from that, to be invested in sort of the future resource stock. So in other words, take all of the profits from oil extraction and invest some of those rents in technology, which in the future reduces our need for oil, right? Since oil is a depletable resource, we don't want current demand and supply of oil to increase demand and supply of oil in the future, because we're just simply going to speed up the depletion of that particular resource. What we want to do instead is we want to take the economic benefits of oil extraction and oil consumption, and we want to invest those in technologies that will eventually get us off of oil, right? So we sort of take the physical capital, the technology that we have, and we use it to offset where we can drawdowns and exhaustion of current resources. So we use coal and natural gas now for electricity generation, but maybe in the future we move to nuclear energy. And we used, of course, the economic benefits of coal and natural gas that added to the ability of us to produce nuclear or renewables or whatever the source is. This also brings into conversation the issue of strong versus weak sustainability, which we talked about previously in the semester. Weak sustainability means that we treat physical and natural capital as interchangeable. So natural capital is natural resources, so oil, water, fish, so on and so forth. Physical capital are things that we put together. So computers, delivery vans, these things are our physical capital. Under weak sustainability, the economic benefit of natural capital and the economic benefit of physical capital are completely interchangeable. In other words, we don't really care whether economic prosperity comes from natural capital or whether it comes from physical capital. It's just we need economic prosperity in order to, give people good lives. Strong sustainability instead says that physical and natural capital are not interchangeable. And in fact, the goal should be to maintain the natural capital stock. So we don't want to draw down the natural capital stock. We want to maintain it over time. And obviously, this puts a strong emphasis on technology, our ability to not only use technology to offset our effect on natural capital, but in fact, use technology in such a way that accentuates the natural capital over time. The problem with this, of course, is that technology often is very natural capital intensive. Going back to the conversation about cobalt, we all love our smartphones, but our smartphones require lots and lots and lots of cobalt, and cobalt is a finite resource, so eventually we will run out of it. And oh, by the way, the extraction of cobalt is an extremely environmentally damaging process. That's another thing that we want to keep in mind. We'll certainly talk more about this, here pretty soon. But the truth is that resource extraction can be very environmentally damaging. So beyond the issues of resource sustainability, we also have the issues of does the extraction of this resource contribute to some other environmental problem? And certainly it does in many circumstances. And then, of course, there's this big issue with intergenerational equity. That is to say that we want to think about resource extraction in a way that ensures that the economic benefits we have today are maintained for those that come after us. So this is sort of related to the issues of intertemporal allocation and Heartwood's rule, where we want to ensure that those that come after us have access to the resources that we had access to. In other words, what this really means is that we should try as hard as we can to sustainably extract resources to ensure that over time, those resources are still around for the folks that come after us. This is especially important in the context of renewables, food, water. We want to make sure that those resources are around for the folks that come after us. There are, of course, some resources for which eventually this is simply not going to be possible. Again, oil, natural gas, we're extracting these resources at a rate, again, that any notion that they could be replaced by some natural process is completely ridiculous in many respects. So again, for those resources, we still want to think about them sort of in a sustainable way, but we know that we're not, for example, keeping oil around for people that come, 1,000 years after us, right? By 1,000 years, hopefully, we have figured out ways to run things that don't require oil, because in 1,000 years, we may very well have access to no economically feasible and extractable oil. Oil rents, so these are two graphs. This is China on the left and the United States on the right. These are rents as percent of GDP. So it shows you how important these resources have been to these two economies over time. So in the 1980s, oil extraction was, as oil rents, I should say, were more than 10% of all GDP in China. And in the US, we can see that in the 1980s for the US as well. And the reason, of course, in the 1980s, oil prices were extremely high. So in the 1970s, we had a series of Middle Eastern political disputes, the first Iraq-Iran war, and several other political and social disputes in the Middle East, which dramatically increased the price of oil. And as a result, many countries saw oil and the profits from oil become appreciably important components of their economic system. I mean, even in the US, with as large as our economy has been, that 3% of GDP more came simply from the profits of oil says something. I mean, you can see that in both countries. Now it's much lower. This doesn't mean that oil is not important. It just means that the size of the economy relative to the profitability of oil has changed. And so oil is certainly still important, but the profits coming from oil are less economically important than they used to be. And I think this is, something that we should point out. Oftentimes, oil, for example, is treated almost like it's a too big to fail resource, where it's sort of treated almost like a jobs program. We think about oil not just from how we use it, but also what it creates in the form of jobs, companies, and so on and so forth. But as you can see, oil in the US has been for a long time a fairly unimportant component of our GDP. And this, again, is strictly those oil profits. But go back to Heartwood's rule. Heartwood's rule should say that any of these profits, what we should do is we should take some of these profits and we should invest them in, so-called greener technologies. in the case of fossil fuels. And then this is, again, going back to this idea that it's not just the resources, but it's how we use them. Electricity generation is one of the most resource intensive economic activities. This is for the US. This is electricity generation over time in the US relative to its source. So this top line is coal. You can see that for the longest time in the United States since the 1960s, coal has been and continues to be the most important source of electricity generation in the United States. It's further declined, and we're seeing this natural gas, which is this red line here. We're seeing natural gas start to take over and really unseat coal as the sort of most important electricity generating resource. The orange line is nuclear. You can see that we saw a brief increase in nuclear as it pertains to electricity generation in the 70s and 80s, but then since the 90s, it's completely flatlined. And in fact, we expect this line to decline. There's just very, very little interest in increasing the role of nuclear energy in US energy portfolio at this point. There's a lot of reasons for that. I don't agree with them. I think nuclear actually is something that we should have really ramped up. I understand that there are issues with nuclear, the waste issue, but it really is the cleanest form of electricity generation that we have in the context of when you actually, use a nuclear reactor to create electricity. It does far less environmental harm than coal and natural gas and certainly oil. And so, yeah, there's the issue of waste, but a lot of technologies improved over time to deal with issues of waste and of course, the issue of nuclear accidents, which I think is the big reason why we've moved off of nuclear. I think people are afraid of it, and for obvious reasons. But it's not just in the US, this is happening in other parts of the world as well. Europe has traditionally had much more. In France, for example, Germany have a lot of nuclear power plants, but even in those countries, you're seeing the role of nuclear decline. In Europe, it's declining in the face of increased renewable energy. In the US, it's declining in the face of natural gas as sort of becoming that new superstar of electricity generation in the US. So let's get into some economics. Let's do some nice sort of mathematical kind of economic analysis here. So let's define a couple things. Let's first define this notion of marginal extraction cost. So marginal extraction cost is the explicit cost of actually pulling a resource out of the ground. So you think about, I want to take out the next unit of the resource, how much is it going to cost me? That's marginal extraction cost. This could increase, decrease, or be constant over time, depending upon the resource in question. Oil, for example, generally gets more expensive to extract over time because you have to dig deeper and deeper into the earth. Water, as a renewable resource, its extraction may even decline over time because technologies may get better and we just may get better at pulling water out of water tables. And so, that could decline, which could be problematic in the context, again, of us extracting water in a sustainable way. But again, it's important for us to have an understanding of what would increasing marginal extraction cost, what would decreasing marginal extraction cost have on the resource use. And really the more important point that we're going to talk about here in a moment is this idea of transitioning between the resources. And we're going to focus on depletable resources because those are, of course, the ones that we're concerned about it, and we want to be able to transition to substitute resources for those particular resources. With renewables, we don't really have to worry about substitutes because as long as we extract those and harvest those in a sustainable way, we can have those in perpetuity. The marginal user cost, this is the opportunity cost of extracting the resource. So in other words, whenever you extract a resource, you think about, you could have done something else with those resources. I shouldn't say resource. You could have done something else with that time and money that you instead chose to extract a particular resource. And so we call this marginal user cost. Generally, marginal user cost rises over time as we extract a depletable resource, because as we extract a depletable finite resource, the opportunity cost of extracting that rises. So each unit carries with it more opportunity cost than it did. And we'll talk a little bit more about why that is in just a moment. And so we just add those up, and this gives us total marginal cost. So the total marginal cost of extracting the resource is the extraction cost and the user cost. And again, where user cost is sort of the opportunity cost of extracting the resource over time. It's important to remember that resource extraction is about profit maximization. There are certainly some countries for which they've nationalized their resource portfolio, but in most places, private companies and under various forms of government intervention, including regulation, of course, but these are decisions being made by private companies. And so there's a natural process to what's going to be extracted first. So least cost resources will be extracted first, and then over time, depending upon the market dynamics of the markets that use that resource, that's going to go on to determine to what rate is that resource extracted, or are we transitioning to another resource that we can use as a substitute. Again, if you go back to this, clearly natural gas is seen, at least in the economics, as a substitute for coal. We're seeing coal decline as an electricity source, and we're seeing natural gas rise. Natural gas is the only curve, by the way, that's actually increasing in this figure. Your renewables, I mean, maybe you call this an increase, but it's been very, very slow. The U.S. is behind, again, those European countries and even some of your Asian countries as it pertains to renewable resource use and for electricity generation. So in the U.S., it's been this rise of natural gas and this fall of coal. So we're sort of transitioning away from coal and towards natural gas. So let's think about this, and let's, again, with an idea that that transition needs to occur in a smooth way so that there aren't any social or political upheavals that may, if we're using coal and then all of a sudden we run out of coal and then we have to go find natural gas to use, that would be really bad, right? There would be a lot of political and human misery in that meantime. So it's important that we develop substitute resources that we use alongside of a depletable resource that we know we're going to transition off of at some point in the future. We have to be very forward thinking with resources. We have to try to avoid being myopic, short-sighted. So for example, burning coal is much cheaper historically than a photovoltaic cell, which comes from your solar energy. And you're easy to get at. Cleaner oil is going to be extracted before you're hard to get at dirtier oil. Again, this is just, in a sense, kind of economic logic, right? Profit maximization implies cost minimization. So we know that the easier to get at resources are going to be extracted first, and then depending upon market conditions, we may move to the harder to reach resources. All right, so in this graph, what you have is on the left, you have just the consumption of a resource occurring over time and to what we call a choke point. The choke point means there's no more of the resource left. And you can see here that choke point occurs in period 9. So this is time periods. So in the 9th time period, we reach the choke point for this particular resource and it's no longer there. On the graph to the right, what we have is an illustration of the costs associated with that particular resource. Now, this resource is a depletable resource that has no substitutes. Okay, so this is a depletable resource for which there are no substitutes. We're going to assume marginal extraction cost is constant. So let's just, for a moment now, we'll assume that marginal extraction cost is constant. Notice that total marginal cost is rising. And again, this is because that marginal user cost, this part of the total marginal cost equation is increasing. So marginal extraction cost is constant, marginal user cost is increasing. This is why we see increasing marginal cost. And so over time, the resource will become more expensive to use, not because it costs more to extract, but because the opportunity cost is growing over time. So every unit that we consume of the resource in periods up to the choke point is causing an increase in the user cost over time. And then we can see here, there's the choke point, and then this is what we call a discontinuous stoppage of this resource. There's just no more of the resource left. And so if we were using it, if it was being used for important reasons, this would present an economically political and social problem, right? So the choke point would cause massive problems. So again, with no substitute resource, there's a discontinuous shift and no transition. That would be really bad. So now let's consider a situation where we do have a transition. We have a substitute resource. So same situation here. This is the line that defines the resource consumption of the current resource. And we see here that there's a transition period transition time in period 6, meaning that at point 6, we transition from the old resource to the new resource. And this new resource is, we're going to assume, renewable. So the first part of this graph we can see is very similar to this graph here. So we have constant marginal cost, increasing marginal user cost, and then at the point of switch, what we see is this smooth transition in total marginal cost and a stabilization of total marginal cost. Now, it's important to realize that this transition will only occur for economic reasons, or if the government says we have to switch to the new resource, right? The government literally says, you can't use this old resource, you have to use this new resource. Let's imagine for a moment that that's not what's going on. Let's instead think that this is going to occur for natural economic reasons. And the fact is that there is a natural economic story that would explain this transition. So if this is the total marginal cost of the existing resource, or what we call the old resource, the non-renewable resource, the reason why we switch to the renewable resource is because now the total marginal cost of the old resource is equal to the total marginal cost of the renewable resource. And so now there's no longer any economic reason to keep using the old resource because it costs just as much as the new resource. And because this is a depletable old resource and this is a renewable new resource, we want to transition to the new resource in a smooth fashion. And as long as we are consuming the current resource at a rate that aligns with the perhaps technological necessities that we would need to move or have this renewable resource. And so, for example, solar. So if we're talking about coal extraction or even natural gas extraction over time, and then we're thinking about the transition to solar, right? What's the problem with the transition to solar? Well, currently it's cheaper to burn natural gas than it is to store solar energy. So what we need to transition from natural gas as an electricity source to solar as an energy source is that we need the technology of photovoltaic cells to become cheap enough that it's now, from an electricity perspective, it's no more expensive to use a photovoltaic cell as it is to burn natural gas. And we will not transition to solar energy from natural gas until that occurs. Now, again, over time, we expect, because natural gas is a finite, non-renewable resource, that we will draw down its stock. When we draw down its stock, this raises the marginal user cost. So the cost of using natural gas should rise over time, and it will rise to the point at which it becomes equalized with the solar technology, and then we will transition to that solar technology, okay? So the reason why the after transition total marginal cost is flatter than this is because the marginal user cost of the renewable resource is much lower. Okay, remember, marginal user cost is the opportunity cost of using the resource. Always has higher opportunity costs to use a depletable resource than it is to use a renewable resource, for the specific reason that every unit you use the depletable resource reduces its total stock, its total reserve. Whereas when you use a unit of the renewable resource, you do not draw down its stock, and so its marginal user cost does not rise over time. So there's another reason why we should want to transition from non-renewable resources to renewable resources, is because renewable resources have much lower marginal user costs that will not rise over time. But what happens if marginal extraction cost is not constant? So in both of these first two examples, I have held marginal extraction costs constant, and we saw that this led to increasing marginal user costs, and then depending upon whether we have a transition substitute, we either exhaust the resource with no substitute, or depending upon the economics of the old resource relative to the new resource, if there's a substitute, we have this potential for a smooth transition, and we avoid all that social and political disarray that would come from reaching the choke point without any substitute transition. So now let's show what happens when we increase marginal extraction costs over time. So again, this is perhaps not realistic with respect to a lot of your resources. Oil, natural gas, as we extract more and more of those particular resources, it becomes more expensive to extract them over time. And so it's a little bit more realistic for us to also consider the outcome of when marginal extraction cost is rising. So again, if we think about society paying for the extraction of that clean Middle Eastern close to the surface oil, and then we juxtapose that with the extraction of that dirty, far from the Earth's surface Canadian tar sands oil, then we can sort of frame this conversation in a little bit more realistic fashion. So if your marginal, so let's jump over here to the right first. So I think it's a little bit easier to see this. So this is your marginal extraction cost. You'll see that it's rising now. And this is your total marginal cost. You'll see it's rising as well relative to marginal extraction cost. So we're using the resource. And then what you'll notice here is that the switch point is a little bit less than the actual transition period. So it looks like we're transitioning to the new resource a little bit before, or at least we reach economic viability of that transition a little bit before the actual switch. And so why is that? Why is it that we see this sort of early transition to the renewable resource? Well, the reason is because marginal extraction cost is rising, which this means is that as marginal extraction cost rises over time, we will reach the choke point earlier, not because we actually run out of the old resource, but because the economic feasibility of extracting the old resource will be such that eventually it's much more cost effective for us to transition to the renewable resource. So in other words, we can dig up Canadian tar sands oil now, right? Or we can think about drilling for oil in the Arctic, which is an extremely expensive endeavor. But if we are transitioning over time away from oil, right, and to other resources, then those increased extraction costs may actually lead us to transition to the renewable resource quicker. This is why it's really important that for depletable resources, we have increasing marginal extraction costs. If we have constant marginal extraction costs, we still can see that transition, but it's going to be a little bit more knife's edge. Whereas if we have increasing marginal extraction costs, then this will, in a sense, economically cause us to transition to the new renewable resource earlier than we otherwise would have. What's also interesting about this is that if you remember, total marginal cost is equal to marginal extraction cost plus marginal user cost. So marginal user cost is this difference between these two curves. You'll notice that in this scenario, marginal user cost is rising over time, whereas in this scenario, with increasing marginal extraction cost, marginal user cost is in fact declining. What this means is that when MEC rises, marginal extraction cost rises, marginal user cost falls over time until going to that transition point. So why is that? Marginal user cost represents opportunity costs of foregone future benefits. But since it's costing more and more and more to extract the resource, this is reducing the future benefits of using that particular resource. And so what we're doing when we have rising marginal extraction costs is that we are reducing the economic incentive over time to consume the resource. Whereas if we have constant marginal cost, or in fact declining marginal extraction cost over time, we are incentivizing the extraction of that particular resource. This is why fossil fuel subsidies are so problematic, because they are going to slow down the transition away from fossil fuels, because they're in fact making extraction costs smaller than they otherwise would be. So when we subsidize fossil fuels, what we're doing is we're causing the marginal extraction of subsidized fuels to decline, meaning that we are slowing down or in fact preventing that transition to non-fossil fuel energy sources, perhaps. It's important to note also that if we have marginal extraction costs, the net benefits of consuming the resource into the future fall. So with rising marginal extraction costs, it in fact at a certain point doesn't become economically useful or economically right-headed for us to continue using the non-renewable resource. Now again, this assumes that the renewable resource exists and is available to us to transition. Right? So we're only starting to see transitions away from coal and into things like solar and wind. What we're instead seeing is a transition of coal into something like natural gas. So if you wanted to think about that, that would be this stock, let's think about this being coal, and then we've started to switch from coal to natural gas. That natural gas line would still be declining, right? Will still be declining. That's okay, as long as eventually, in maybe periods 10, 11, or 12, we eventually transition to solar or wind or renewables or something like that. And so if the government is incentivizing natural gas exploration by subsidizing natural gas, by arguing that, well, since natural gas is cheaper than coal, we would prefer it, I think that's smart from a pollution perspective because natural gas is certainly cleaner than coal. However, this could potentially cause us to use natural gas longer than we would have had we not subsidized. Right? So that's the problem with subsidies for energy, is that they may put off the transition period. They may reduce the smoothness of that transition. And of course, what we're interested in is transitioning to the renewable resource in a nice, smooth way. And hopefully we leave as much of that old resource in the ground as possible, especially considering that those resources create their own environmental problems. Oil, natural, even though natural gas is much cleaner than coal, it still contributes to climate change, for example, although at much lower rates than coal does. So it's not completely clean. It's cleaner, but it still has an amount of social damage that, if we can avoid it by switching to solar and wind or other sources, we certainly would want to. So when the marginal extraction cost is constant or falling, we will exhaust the resource before transition potentially. And again, this is highly problematic. So it's important that when we're extracting a resource and we're getting closer and closer to its exhaustion point, that the market react in a way that increases those marginal extraction costs. If the government is instead fighting those increasing marginal extraction costs because of political lobbying by the fossil fuel industry, this is potentially devastating to our ability to transition to those new energy sources. We could, of course, tax the old resource. This would speed up the transition. We could subsidize the newer resource. That would speed up the transition. But if we subsidize the old resource, we absolutely will slow down that transition. And unfortunately, this is a lot of what not just US policy, but the global policy as well. Technology matters over time. As technology improves, marginal extraction costs could decline naturally. It's just cheaper probably now than it used to be to extract oil. So that is going to put upward pressure on the amount of oil that we extract. And this could speed up the exhaustion of that particular resource and do so in a way that doesn't prepare us for that transition. And so technology that's being used for the old resource can be problematic over the long run. A really good example of this is known as Jevons paradox. William Jevons, Jevons, was an economist in the late part of the 1800s, early 1900s, and he was doing work in coal. And what was going on in that time period was that the government, as well as private industry, were trying to produce, ways to make coal burning more efficient. And the idea was, if you made coal burning more efficient, you wouldn't need to burn as much coal. Well, what Jevons said, and he was right, is that if you make coal burning cheaper, you're going to burn more of it, right? There's a sort of an inherent economic logic that says that if you make something cheaper, you're going to do more of that thing. And so Jevons sort of correctly predicted that if you make coal burning cheaper, you're not going to burn less coal because you get more coal electricity out of each unit. You're in fact going to increase the amount of coal burning that you will do. The same thing with fuel efficiency in automobiles. Fuel efficiency, primarily through the corporate average fuel efficiency standards known as CAF standards, are often sort of put up as an example of policy that could potentially reduce, climatic effects from fossil fuels. But the fact is that when we make cars more fuel efficient, we've made driving them cheaper. And again, economically, when you make something cheaper, we expect to do more of it, not less. And so we have to really think about the way that policies interact with the profit maximization process of these resources, which is also sometimes why a lot of people think that we should nationalize resource, and make that decision not a private decision, but instead make it more of a collective decision. And all I can tell you is that where that has been done, Venezuela is a really good example of this. The nationalization of those resources has not ended up well for that particular country. And so, the idea that if you just remove the profit motive from oil extraction, you solve all the problems. No, the way that you solve these problems is you make sure that the profit motive of oil extraction aligns with what your vision is for social prosperity. And so if that vision of social prosperity is we're going to transition away from oil to some other resource, you want to make oil extraction more expensive over time, not cheaper, and you want to technologically prepare yourself to transition from oil to some other resource. That's how you take care of that particular problem, in just sort of a straight way. Now, how you do that, the specific policies, there's a lot of options there, but it doesn't need to be this rejection of the profit motive. It just needs to be a situation where government intervention, and the broader market itself is structured in a way to ensure that the profit maximization that's occurring is being done in the context of that transition plan, to the new resource. This is, of course, why you see companies like Exxon and BP, they're investing a lot of money into renewable technologies, right? Because they see the writing on the wall. They know people, would like to get away from, oil technology. And so you're seeing those companies now invest tons and tons of money in renewables. The more cynical among us may worry that they're doing that to squash those endeavors. It remains to be seen, of course, if that's what's going on. But I'm optimistic that they're doing this because they see that there's profit maximization that exists in renewable energy. And so, in fact, they're in search of profits is going to lead them to invest in renewable energy, and already has done so. Again, I'm not saying that this isn't a free market argument at all, right? There's still a litany of problems with resources in the free market. But what it says is that we don't have to necessarily see the profit motive of resource extraction as being the root problem. What we can do is we can condition the atmosphere of resource extraction to make sure that our goals as a society are embedded in that. So if we want to transition to new fuel, we tax existing old technologies that are dirty, and we subsidize newer technologies which are cleaner, right? That's going to speed up that transition, and again, it's going to align the profit motive with the broader sort of social strategy when it comes to prosperity. One of the things that we can do is we can include into the extraction cost the environmental cost of extraction. So this would be something like a Pagovian tax put on the extraction of a resource to heighten the understanding of the extractor of the true cost of their extraction. Or in the case of, say, fish, we can have fishing companies pay for fishing permits, which again takes some of that externalized damage that comes with overfishing, and they internalize it. And so now, if we make them pay for every fish that they catch in some way, then this reduces the profits of catching fish to some extent, and means that they may seek out other means of economic prosperity. And this may have the natural effect of ensuring that fishing stocks are more sustainable moving forward. Then here are just some graphs to wrap up this particular section. So this is just the same graph as before, electricity generation. I've just taken out everything but coal and natural gas. I like this graph. It really reminds me of those political horse race graphs you see on cable news. Support for one candidate, then support for the other candidate. But I think this graph is really explanatory as to the U.S. Revealed preference as it pertains to these strategies, and that is that over time we're using less coal for electricity, and that is being substituted for with natural gas. So we are transitioning from coal to natural gas. Now, the truth is that this means that we're transitioning from a depletable resource to another depletable resource, right? So it's not perhaps the greenest transition that we want. We're also transitioning from a resource that creates external damage to another resource that creates external damage in the form of pollution. And so, we're trading, real bad for less bad, but that's an improvement. And I think that we should look at that, and we shouldn't be so cynical about it. This transition is causing a dramatic reduction in CO2 emissions coming from electricity, right? So we're producing less CO2 emissions from electricity because we've transitioned away from coal and into natural gas. So that is definitely a benefit of this particular transition. Now, again, hopefully we transition away from natural gas and quickly into renewables or nuclear or something like that. This tells you where the energy sector uses these particular resources. So you can see how big they are relative to major sources over time. And again, tells a very similar story. Renewables, nuclear, your cleaner technologies are just not used as much. Coal, natural gas, crude oil, your dirtier technologies are used in great abundance. Why is that? Because it's cheaper to use them. There are more profits in these areas at current technology levels than there are profits in these particular areas. And in the case of nuclear, some of this absolutely is market intervention in the form of the government not giving out nuclear, permitting for nuclear reactors to be built. There's also, of course, fossil fuel subsidies at play here as well. And so the dynamics here are not just these resources, but also the policies that surround them. And this might be hard to see, but this just shows you, where the particular type of energy source is going to. So in this scenario, we have, a lot of your energy is going to transportation, industrial issues, electricity issues as well is a big source. So about 26% of all energy goes into transportation. About 24% comes from electrical needs as well. But this just shows you where these particular sources are going. So you can see natural gas going primarily to transportation as well as electricity generation. Petroleum is going primarily into transportation. Your renewable energy is, again, primarily going into transportation. Unfortunately, very little renewable energy is making its way into electricity these days. And then perhaps a bit of a good thing is that we're seeing coal as a sort of part of the broader energy timeline decline.